also I will give some definition of multivariate Rényi divergences, which I think is something that I haven't encountered. Did you share so far? Yeah, at any point if you have any questions, feel free to interrupt me. Okay, so we have already seen some Rényi divergences in Anna's for instance, but I will very quickly go over the main definitions, especially because we are going to consider more general notions of Rényi divergences. So we're going to consider multivariate quantum divergences, which in the most general setting, we have a variable set index by some set x. And this is just, a divergence is just a function that maps a collection of positive semi-definite operators to a number. Okay. So this is the zeros level. We also require that it's invariant under isometries, right? I'm going to use this strange notation, so quantum states are going to be denoted by W. This comes from this classical quantum channel called in literature. More generally, they can be positive semi-definite operators, right? So if you put all these operators into a larger vector space by an isometric, then the divergence should be changed. Okay, so this is also a very reasonable requirement. And of course, then it uniquely extends to more abstract filter spaces, not only to c to the power t. And in special case, when we have a two-variable divergence, then this x set is just 0, 1, and I'm going to use these notations which are more familiar in the literature of quantum divergences. Okay? So I'm going to denote the states by rho and sigma as they should be. Right. Very often it is already known in the classical case what kind of divergences we should be interested in. So the question is how to extend them to the quantum case, right? So we can talk about classical divergences, which are the same kind of objects just defined on commuting operators having these functions. And we say that a quantum divergence is a quantum extension of a classical divergence if when we take a collection of functions on a finite set and an arbitrary orthonormal system, and we put these function values onto the diagonals of matrices, and we create this collection of operators, then the quantum divergence should take the same value as the classical divergence on this set of functions. Okay, so this is again very straightforward. It's worth noting that there are always some quantum extensions, right? So whatever classical divergence we start from, we can always define the so-called measured and maximal extensions. And both are somehow connecting in a very straightforward way to the classical setting. So in the case of the measured, we're mapping our operators into commuting operators by performing a POVM measurement. And this is the post-measurement probability distribution. And we are optimizing over all such possible POVMs. Okay, so this gives us a quantum extension. And a maximal extension is somehow the dual notion when we are trying to find commuting objects and map these commuting objects into our non-commuting objects. Take the classical divergence of the commuting objects and take the right? So they are obviously dual to each other. And it's very easy to see that they are extremal in the sense that by definition they are monotone under actually PTP operations. And the first one is minimal and the other one is maximal with respect to this property. Right? So these are canonical and they have these extremal properties. Sometimes we are interested in some variations of these. And for instance, for Rényi divergences, it makes sense to regularize them. Okay, so we do this procedure for every large enough tensor power of these operators and take the limit of this regularized quantity provided that the limit exists. And normally it would exist, right, if it's a reasonably nice divergence. And these are again extremal. The first one is minimal, the other one is maximal with respect to those quantum extensions that are not only CPTP monotone but also weakly additive. Okay, and this weak additivity again follows by definition. Okay. There's no guarantee that it is strongly additive. Right? So if we take different collections of operators, then we would need not have additivity. Okay, so these are still very abstract. And what we are going to be interested in is Rényi divergences. So you have already seen the definition. Let me repeat it in the classical case. In the two-variate case, if we have two non-negative functions which are non-zero. Then we define this Q alpha quantity, which is just it's defined as it is written here. And this is what we actually care about mostly, and then we can put it into different other functions. For the Rényi divergences, we put it into the logarithm divided by the scalar normalized. This simply state. We have seen the definition with size divergences, which is like variation. But what matters is really this quantity inside. Okay? And when these kind of normalizations come into play, for instance, when we take the limit alpha goes to 1, so obviously this only makes sense for alpha not equal to 1, it's very easy to check that then we get the normalized relative entropy or Kalbeck-Leiter divergence, which is defined by this formula well known to everyone, and it's just divided by the trace. What is probably less known, and actually it seems to be surprisingly recent, I wasn't aware of this, that somehow it goes the other way around too. So this is a one parameter family of divergences, and the relative entropy is one single point on this curve of divergences. And it seems that we can recover this whole curve by one single point on this curve. So if we know the relative entropy, then there is this very simple variational formula from which we can recover all the alpha Rényi divergences. Okay, so in this sense, the relative entropy is the only one we should care about, because from that we can generate. Okay. And this formula is going to play a very important role in the talk. Okay, and one last thing I would like to mention is that in the classical case, it's very easy to define a multivariate generalization. So instead of this Q alpha quantity for rho and sigma, we can take again a number of commuting diagonal operators, positive semi-definite, and we can take arbitrary weights, real weights, which sum to 1, and then we can define this quantity. This is well defined because all these operators commute, and obviously this is an extension of this one. And we would like to consider negative weights also, because here there is only this parameter alpha, but of course this is also a probability distribution, alpha 1 minus alpha, but this 1 minus alpha can be negative when alpha is larger than 1. Right? So also here we might want to allow negative weights. Good. Okay, next I would like to talk a little bit about why these quantities are important to us. You have already seen some of this. I talked about this thing at many places, but let me very briefly go over this. So Rényi divergences are important because they appear in exact quantification of trade-off relations. So in many information theoretic problems, we have two quantities which are somehow competing with each other, and we want to quantify the trade-off between them. This is the simplest example of state discrimination. I guess all of you know it. We have many identically independently prepared systems. Either all of them are in state rho or all of them are in state sigma. And we are allowed to make two outcome measurements on many copies of the system, and we record the error probability, or we compute the error probability of erroneously rejecting the hypothesis that the true state is sigma, or the other way around, erroneously rejecting the hypothesis that the true state is sigma. And it turns out that we can choose these measurements for larger and larger number of copies, such that the error probabilities go to 1 exponentially fast. And then we are interested in what kind of error exponents we can achieve. So it's a point on the plane, and it turns out to be this region, and it can be described obviously by describing the boundary of this region. So these are the best achievable exponent pairs. And if I denote one of the exponents by r, then the largest other exponent can be expressed by this formula. It's a function of r. The exact expression is not important to us. What's important is that it's expressed in terms of these so-called Betz type Rényi divergences. This is what we have seen in Anna's talk. So this is the definition for Betz type Rényi divergences. And this is an exact characterization. So this is an exact operational interpretation. It's not given by inequalities, it's an equality. Okay. And there's also another part of the story. So when we take this r larger than the relative entropy, so this is the kind of threshold here, then these errors are no longer going to 1, they have 0, the errors are going to 1, and we are interested in the speed with which we are going to 1. This is again exponential, and the best exponential rates are again given by such a curve, the equation of which we can express in terms of another family of quantum Rényi divergences, the so-called sandwich Rényi divergences. Okay. So these two Rényi divergences appear in the quantification of the trade-off in this problem. Normally, let's say in an introductory information theory course, one would see only a so-called first-order coding theorem. So the standard Stein's lemma says that if we are looking at the relative entropy and we take any rate smaller than the relative entropy for the type 2 exponent, then we can achieve that the type 1 errors go to 0. And above this rate, the type 1 errors are going to 1. So this would be a standard Stein's lemma, but this is only a single point on this trade-off curve, right? So this is, if you want a complete solution of this problem in the asymptotic IID case, then we really have to determine this whole curve. Okay. And this is where the Rényi divergences come into play. And this is not specific to state discrimination, so actually there have been a lot of other problems where these exponents have been determined. And listed a few here. Only those problems where at least the complete direct exponent region or the complete strong converse exponent region has been determined. I'm almost sure that I'm missing a few tasks here and probably a few references, so if you have anything to add, then please let me know afterwards. But at least you can see that there are quite a large number of information theory tasks where this has been achieved. And in fact, in many of them very recently, so you see all these results from 2022, and they're very nice and very interesting ones, but I don't want to go into them now. What is worth noting that all of these trade-off relations are in terms of information measures like divergences or entropies or conditional entropies or mutual informations, whatever, but invariably they are all derived from the Petz type or the sandwich Rényi divergences. So this seems to suggest that these are the only two kind of quantum Rényi divergences that you need to care about. So one might ask why care about any other, and I would like to try to convince you that we should care about other quantum Rényi divergences by giving a few examples that don't fall into these two families, and yet they turned out to be quite interesting for information theory. So one of them is this so-called log Euclidean Rényi divergence, given by this very simple formula. Obviously, this is again a quantum extension of classical quantity, and it turns out to be a very useful tool, kind of intermediate quantity, when we want to extend classical coding results to the quantum domain. And first we can get the exponent somehow in terms of these quantities, and then with some manipulation we can arrive at the right quantities. Okay, another interesting thing is that this quantity is not monotone when alpha is larger than 1. Okay, so this is some property that if a divergence doesn't satisfy it, many people would not even call it a quantum divergence. They consider it so important. But actually these quantities are important for this range in the strong converse proofs. So they have found use in scenarios where they are actually not monotone. Okay, so we like monotone divergences, but we don't insist necessarily that they have to be monotone. Okay, there's this other one which was introduced by Hamza and Omar Fazi a few years ago, which is given by this optimization expression, where this is the so-called Kubo-Ando weighted geometric mean, which I'm going to define a little bit later. So here you can see the definition. It's been shown that this is monotone under positive trace preserving maps. It is not additive. Well, okay, this quantity would be multiplicative, but the corresponding Rényi divergence is not additive. So again, people might complain that this is not a good divergence, but even worse, there's no explicit expression for this. Right? But still, it turned out to be very, very useful to study channel divergences. So it was used to establish the strong converse exponent for channel discrimination. And also it has the remarkable property that after regularization, we get back the sandwich-Rényi divergence. Okay, so even though originally it doesn't look so nice, no explicit formula, not additive and so on, after regularization it becomes one of the most important Rényi divergences. And it's very useful in establishing this result. Okay, and the last one I want to mention is a very recent one, introduced by Frankel and later rediscovered by which is given by this kind of integral expression. Okay, well, it doesn't really matter what the exact expression is, but again, it's not really a closed formula. It is monotone, but it's not additive, and it's known that it's not equal to either the pets or the sandwich. Okay. But it turns out, this was shown by Hirhen Tamamichel, that if you regularize it, then miraculously we get back either the pets type or the sandwich type, depending on the value of alpha. Right? And this is very remarkable because this is exactly the range in state discrimination where the pets type Rényi divergence is irrelevant, and this is the range where the sandwich type is relevant. And this was a little bit of a mystery why this separation happens. And now we have this parent quantity that does exactly this. So it just does this separation. Okay, so again, this is yet another quantum Rényi divergence, which doesn't necessarily have nice properties, but it turns out to be very nice. Okay, and the last application that I want to mention, it was already mentioned in Michael's talk, this is state conversion. So many tasks in information theory can be phrased as a state conversion task. We have a finite number of states given, and we want to transform them into another finite number of states. We want to find the CPTV value. This is satisfied. Okay, and in various scenarios, resource theories, whatever, there might be other restrictions on this phi. Might have to respect some symmetry. Might have to be one of these decoherence respecting maps that were mentioned by Anna, or whatever LOCC operations, you can thermodynamic operations, whatever. But here we are sticking with the simplest case where there is no such restriction. But in any case, if this is true, if we can map this set of states into this other set of states, and we have a monotone divergence, then this inequality has to be satisfied. So this is obvious. Okay, and this has been used for two variable divergences, but of course it has to hold for any multivariate divergence as well if it is monotone. Right, so this is a necessary condition, and as Michael already mentioned, there are other versions of this problem. For instance, we can use a catalyst. So then the problem is this: we have to find not only a map, or we are allowed not only to find a map, but also use this catalyst. And here, an obvious necessary condition is that this monotonicity has to hold for any divergence which is monotone and additive. Okay. And finally, as we have seen already, we need not want to arrive exactly to these states, but we might allow some small error of epsilon. Okay. And then this monotonicity has to be satisfied by any quantum divergence that is monotone, additive, and lower semi-convergence. Okay, that's also again easy to see. It's quite nice to see how these rather abstract mathematical properties keep popping up by this very operational requirements. Okay, but these are only necessary conditions, and of course there are tons of them. But what's very interesting is another very recent result by these authors, who showed that if all the states commute, then actually this condition, this monotonicity, becomes also necessary. Okay. No, sorry, sufficient. Right? So they showed that this monotonicity, if it is satisfied by every multivariate Rényi divergences, where all the weights are either non-negative or one of the weights is larger than one and the other weights are all negative, then we can find such a procedure for characterization. Okay, so this is an if and only if characterization in terms of multivariate divergences. And this gives some motivation to the question, how can we define quantum multivariate multivariate Rényi divergences. And it has to be mentioned that this kind of results have been shown in other problems. There are these Klimesh-Turgut conditions, or the second laws of thermodynamics, where these are characterized, but always only for commuting states. Okay, so the general quantum case is, as far as I know, is completely wrong. Okay, so the question is, how can we define multivariate divergences? So our goal is going to be to find Rényi divergences, binary as well as multivariate, with good mathematical properties, and connect them to trade-off relations or state convertibility problems if possible. Right? This is a very ambitious project, right? So this is covering most of Shannon theory. Today I'm only going to talk about a little bit, a small part of the first one, right? The rest was motivation for considering this. Okay, and now for a second I want to get rid of this. I've used the other blackboard, but I didn't know that we can only use this screen. And I would like to sketch a very general, kind of research agenda. How to define all sorts of quantities that are interesting to us, or to some people at least. Okay, so here I've drawn this picture, and everything works as long as we are in the commuting scenario, right? So I'm showing how different kind of quantities are related to each other. I'm going to start from here, so there is a notion of multivariate geometric mean, and this is how we have to define it, right? So these are the weights, these are the object that we have to average. Okay, and this is well defined because everything is commuting. From these, we can obviously, two-variate is a special case, right? I just changed the notation. It's the same kind of thing. And from all these things, we can take the trace. And of course, if these were numbers, then nothing would change. But these are operators. So here we get a multivariate Rényi quantity, again, well defined in the commuting case. Or two-variate Rényi divergences are a special case. Okay. And then there is something called the multivariate weighted power mean. Okay, so these px's are now going to be the weights, and there is also an alpha. So this might be a little bit unfortunate notation, because before alpha was a special case of these px's, but now it plays a different role. So what we do here is two things. Once we have a two-variate geometric mean, we can look at this fixed point equation. Okay. So in general, this would be an operator equation. We are looking for the tau that satisfies this fixed point equation. And it's very easy to check that in the commuting case, any such tau, well, there is a unique solution, and it's this multivariate power mean. Another way to arrive here is to consider Tallis divergences. These were introduced in Anna's talk. And look at these optimization problems. So I'm going to draw a picture because I'm going to talk about these quantities a lot. So we have a set of states, wx, x1, w, wx3, and so on. We can take a state which is now denoted by tau. Well, later it's going to be omega, but anyways. And we compute the distance of our states from this tau, and we also have some weights, P1, P2, P3. Okay. And in this case, we compute the distance with respect to the Tallis divergence. Okay. And this is called, if we minimize this quantity, it's called the divergence radius of this set of states. Okay. So if this was a proper norm, then somehow this would be the radius of the smallest ball that encompasses, that contains all these objects. So this is why it's called a radius. And in this case, we are using the Tallis divergence to compute this radius. And the optimal, this should be a gamma, okay. So Okay. And the optimal state, so we can move this gamma around so that we minimize this average distance. And the optimal gamma is going to be this weighted power mean. So from two variate Rényi divergences we can get the power means. And another easy exercise is to check that if here we take alpha go to 0, then we get back to this multivariate geometric means. I'm going to continue with other things. Okay, maybe I will finish that first. So of course again here we can take a trace, then we get a scalar version of this. And the same way, if we take alpha go to 0, then we get the scalar version of, well, we get these multivariate Rényi divergences. And once we have two variable Rényi divergences, we can define relative entropies simply by taking the limit alpha goes to 1, the alpha rho sigma. So that gives us a relative entropy. And once we have a relative entropy, we can define these two quantities, where here you can again see this kind of divergence radius. Okay, but now with the relative entropy, and there's also a big difference that here the fixed states, the given states are in the first variable, and here they are in the second variable. And that's a very important difference, which I'm going to talk about more later. But again, we get this divergence radius, and it turns out that this is going to be equal to minus log q alpha, and q alpha can alternatively be expressed by this kind of variation expression. Okay. And these are going to give us multivariate Rényi divergences, but also the optimal tau here is going to be a multivariate geometric mean. So what's the point of this circular kind of things? Right? If I start somewhere, I go around and I get back to the same place. That's not the point. The point is that we can pick any point in this picture and try to quantize it. And then starting from that point, we can try to define the other quantities. Okay. And I mean, some part of this, like this area here, has been very intensively studied in matrix analysis. Okay, so there's a huge literature of multivariate geometric means. And also this fixed point approach has been studied a lot. And this is a huge literature which I actually don't know too much about, but there are many results relating to this. Today, I want to talk about this part of the board mainly. Okay, so how to define multivariate Rényi divergences using this kind of quantities. Okay, and what we mean by this quantization is, for instance, here we can formally write up, for instance, objects that we use to the two variable weighted geometric means when the operators are commuting. So we can write up this kind of formulas. You might know this from the so-called Rényi alpha z divergences. This is this alpha weighted Kubo-Ando geometric mean. This is another version of non-commutative weighted geometric mean, which I mentioned before. And for instance, we can start with these things and try to follow this procedure here. Okay, this is one thing I wanted to talk about, and before I continue, I also wanted to draw a picture about two variable Rényi divergences. This is the picture of the two variable quantum Rényi divergences that we know. So these are the so-called alpha z Rényi divergences, which you define by taking the trace of this and putting into the logarithm and whatever. Here are the measured Rényi divergences, which are the smallest one. here are the maximum, which are the largest one. And in this picture, for every alpha and z, we have a quantum Rényi divergence, and I indicated the ones that are monotone under CPT. Okay. And here I distorted the picture, so instead of z, I put 1 over z. Okay, this is so that when we are going upwards, the Rényi divergence increases. Right? So if we are higher on this picture, then for a fixed pair of states, we have a larger value of these Rényi divergences. And the alpha max is the largest, the alpha measured is the smallest. Okay, and for instance, this here is the regularized Rényi divergence, and this part is the sandwich Rényi divergence. So this picture is not good. It should be like this, 1/2. Okay. Right, and what I'm going to talk about today is two kind of things. Yeah, so what I should still mention is that here is the maximum Rényi divergence. Here is the omega k Rényi divergence. You have seen the definition already. And what's worth noting, no. Sorry, it's at alpha equals 1. Here, and here. Here there is something else. This is the measured Rényi divergence. Okay. And you see that there are loads of quantum Rényi divergences, but somehow there are very few relative entropies. Okay. Actually, I only know about 3. Right? And this one is not additive, so if we want monotone and additive, then we only have 2, the maximal and the omega k relative entropy. And in this whole line, it's easy to show that if we go to 1 by alpha, then we always get the omega k relative entropy, no matter what z is. Okay, so somehow this looks strange that this is the most important quantity, and still there are very few, well, only 2 relative entropies that we know. Of course, you can always take convex combinations, so then you get a trivial way of getting new relative entropies. But what I want to show today is a different way of getting new relative entropies, which interpolate between the omega k and the maximum relative entropy. Okay, so I want to define a new family of relative entropies, continuous family of relative entropies. And another thing I want to do is to define a new set of quantum Rényi divergences that are strictly above this d alpha plus infinity, but strictly below this d alpha max. Okay, so in this region we define a new family of quantum Rényi divergences, and also this kind of construction extends to multivariate Rényi divergences. Okay. Let me start with the first one, this definition of new relative entropies. So the general...
Could you remind me of the D max?
The D alpha max or the D max? This is the Belafin-Stashevsky.
I think just the D max.
Belafin-Stashevsky relative entropy. But it sounds so important. Maybe after. I'm a bit short of time, so.
Okay.
But yeah, well, it's also expressed in terms of maybe it's better to okay, so the general procedure is if we start with an arbitrary quantum relative entropy. So this could be the measure, the omega k, the maximal, or whatever anyone might find in the future, and we take a non-commutative two-variable weighted geometric mean, and we define this very simple formula. So we keep rho, and in the second argument we get this. We put this weighted mean of the 2 arguments and divide by 1 minus 1. Okay. I mean, it's straightforward to verify that this is indeed a quantum relative entropy. So it reduces to the usual Kalber-Kleiber divergence on commuting things. And what we are interested in now, or what we we choose this weighted geometric mean to be the so-called Kubo-Ando geometric mean. Okay, so it's defined by this formula, and this is what we put in the second one. And then we want to examine the properties of this quantity. Because this mean is additive, then if the original relative entropy was additive, then so is this variant. This is very easy to see. And monotonicity is also very easy to see. Actually, we don't need it for a class of maps, just a single map. If dq is monotone under a single map, phi, and it has this property that it's anti-monotone in the second argument, which all the relative entropies we know have this property. Then it's a three-line computation to show that this variant is also monotone under phi, because we just write in the definition these geometric means have this kind of monotonicity property. This is very well known. Then we use the anti-monotonicity in the second argument, and then we use the monotonicity of the original Q, and we are done. Okay. So monotonicity we get for free basically, and because we know that the omega key is the smallest and the maximal is the largest relative entropy that is both monotone and additive. And if you start with anything else, which is also additive and monotone, then it has to be between the two. In particular, if you take dq to be the omega key, then we have to have this inequality, and if you take dq to be the maximal, then we have to have this inequality. It is also clear that with this procedure, a larger relative entropy generates a larger sharp gamma relative entropy. So for any q in between omega p and maximum, we will have this chain of inequalities. Okay, and it turns out that for the maximum, we don't get anything. Okay. So if we take this sharp gamma variant, nothing changes. Right? But using this first inequality, it's not too difficult to show that if you start with the omega key, then actually you get an increasing relative entropies. And one can show that if this gamma parameter goes to 0, then we get the original omega key. If gamma goes to 1, then we get the maximum. So we really do have this kind of interpolation between, I cannot go to the board, but I draw on that board, right? So it interpolates between the omega key and the maximal relative entropy for, at least for invertible operators. Okay, what happened here? Yeah. Yes?
This Kubo-Ando operator mean you can use an arbitrary operator monotone function. Does this go through, or does this not give anything reasonable? No generalized relative entropy in this case.
I mean, where do you want to apply this operator monotone function?
Everywhere.
Everywhere. I mean, yeah. So if you want to get a relative entropy, then you have this constraint that it has to be due to the classical Harvard-Library divergence. So you have to have a formula which has this property, right? So it will probably not work with an arbitrary function. But of course, you might get other quantities which have nice properties. Right now, let's see how this happens. But here I specifically want to get quantum relative entropy. Right, and because of the sandwich property, if we get this limit for the omega key, then we get the same limit for an arbitrary, and starting with an arbitrary quantum relative entropy. So when gamma goes to 1, it will always be the maximum relative entropy, and when gamma goes to 0, it will be the original. So this construction always interpolates between the original quantum relative entropy and the maximum. Okay, this condition that the states were invertible very important. So for instance, if the first argument is a pure state, then it's again easy to see that all these sharp gamma omega key relative entropies are the same as the max relative entropy. But without this modification, we get something strictly smaller, right? So in this case, we don't have this interpolation. We have a jump right after 0, which is not so nice in some sense. But on the other sense, it is nice because it allows us to show that we really get something new. So I already mentioned that one trivial way of interpolating between two relative entropies is to take convex combinations. Okay. So here we can do this. We can take convex combinations of the omega key and the maximal, evaluate it on this pair of states, and because the omega key is strictly smaller than the maximal, this convex combination will be strictly smaller than the maximal. Okay, but we have just shown, or I told you and hopefully you believe, that this U gamma sharp coincides with the maximal. Right? So for any pair of P gamma between 0 and 1, there's going to be a sharp inequality between these two. So no convex combination of these two relative entropies gives us this the U gamma sharp. Sharp gamma. Okay, so this is really a new family. The U gamma sharp is not the same as 1 minus t du plus t times d max for any t and any gamma.
You have example where it's positive definite? Because this only shows it's different.
Yes, so it might seem like a pathology, but all these have very nice continuity properties, so it's very easy to get positive definite examples. So yes, thanks for the question. Okay, so this was the first project that I wanted to explain. The second one is these barycentric Rényi divergences. So this is the new family of quantum Rényi divergences, and which immediately generalized to multivariate ones.
So that was only for the pure state? Maybe I missed.
Which one?
That before? That you want the first argument to be general.
So we want to show that these two objects are not the same, right?
Ah, okay. So it's sufficient to show it on the pure state that it's not the same, and
For
then
any pair of arguments.
and then yeah, okay,
Yeah.
understood.
Yeah. So as functions, they are.
Yeah, it's okay.
Right. So here we have this general setting that we have a set of positive semi-definite operators. Just for technicalities, we might need to care about these support projections, but for the moment you can forget about them, they are not so important. And we define these two variational formulas. So actually this is our definition. This might be maybe less obvious to see why we choose this to be our definition for this. So this is the multivariate quantum cube quantity. And it's a little lemma to show that if you take the negative logarithm, then we actually get this variation expression. And we have already seen that in the classical case, this gives us the proper Rényi quantities that we care about. Okay. And again, here you can see that this is one of these divergence radius quantities, right? So this is what's written here. And here we measure the distance by a relative entropy. Okay, so this is why I wrote, this is the radius corresponding to this quantum relative entropy, and this is left because we put the variable omega to the left. Okay. There's also a right version. Right, so this is our definition. And just from the definition, basically all the important quantities can be verified. So, yeah, I mean, this is this one is a supremum of affine functions on P, so it's going to be convex, same with the logarithm. But many of the nice properties only hold if P is a non-negative, so it's a proper probability distribution. But if all of the QX's are monotone under some map, then so is this Rényi quantity. I work with this minus log QP because in the two variable case we divide by this quantity by 1 minus alpha. But yeah, in the multivariate case, actually that factor is not relevant. It's only the sign that matters somehow. Okay, joint convexity is also inherited. Lower semi-continuity inherited. What is not inherited, unfortunately, or we don't know if it's inherited, is additivity. Okay, so if all our relative entropies are additive, then it's trivial from the definition that this quantity is subadditive. And subadditivity means that if I have the same, so you can think of these W's as classical quantum channels, right? So if we have two classical quantum channels with the same input alphabet, then we can look at this channel that outputs these tensor product states, okay, in each input alphabet. Then we have this subadditivity property. Okay. And the big question is additivity, and sometimes we can show it. So if we start from the omega key relative entropy, then actually we can explicitly express the optimal omega and the value of the sink. And what we get here is just this exponential average of these W axes. Okay, so this we can solve explicitly. And it's trivial to see that this is actually additive. Okay, this is nice. And I want to comment about where we put this omega, right? So we have this expression here, and here we put the omega in the first argument and the fixed W axis into the second one, but we can do it the other way around. Okay. And what we get by swapping the order is actually nothing else, so I call it the right divergence radius. This was the left divergence radius. It's just the well-known Hollywood quantity. Right? And in that case, we can determine the optimal state. So here we assume that all these W axes are actually density operators. Otherwise, we have to do some normalization here. Okay, so again, in this case, we can explicitly express everything. And we have additivity, but we have a different kind of additivity. Okay. So here we defined one notion of the tensor product of CQ channels, but when we think really of them really as channels, then you can actually take channels on two different input alphabets, and you can define the tensor product channel as a channel on the product alphabet, right? And on each pair of inputs, it outputs this kind of tensor product where these input symbols can be different. Okay. And in this case, you also take the tensor product of the input probability distributions. And the whole Evo quantity is additive under this kind of tensor product. And this is very, I don't know, in some sense mysterious, some sense very nice to me, that it's not obvious that just because of changing this order, we should get something so different. But in the same time, this kind of tensor product is the natural tensor product for state discrimination. So when you study state discrimination, then you have a fixed set of messages encoded into quantum states, and you look at larger and larger tensor powers. But you don't change your number of messages, you don't change your set of messages, and you want to read out this information. So the natural quantity for state discrimination is this kind of tensor product of classical quantum channels, and the natural related quantity is the Rényi divergence, which respects this kind of tensor product. But for channel coding, the natural thing is to use this other kind of tensor product where you can use sequences of input symbols, and at each instance of the use of the channel, you can choose a different input symbol. And this quantity respects this other kind of tensor. So, okay, it's just a comment that I found interesting. And of course, we can define the two-variable case. So what I explained before, it was the multivariate case. If you restrict to the two-variate, then we get the same. I mean, this is just the special form of this formula that we defined before. And here we just have this extra normalization of dividing by 1 minus alpha and subtracting this trace term. Okay. And in this case, we might ask some further questions. For instance, convexity and alpha, which is very important usually when we deal with these quantum Rényi divergences, and also monotonicity and alpha, which is another important quantity. And we can ask about the limits when alpha goes to different values where these quantities are not immediately defined. And it turns out that if alpha goes to 1, then we recover one of these parent quantities. So there are two. Okay, so something I didn't emphasize. So in this divergence radius thing, you can use generalized divergences, but for instance, the relative entropy. But you can also choose a different distance for each of these states, right? And this is what we do here, right? So we have a dq1 and a dq0. So we might use different relative entropies to measure the distance of the different states. And if alpha goes to 1, then we recover one of these parent quantities. And when alpha goes to 0, then with some combination we recover the other. Okay. So this also means that if we start with different relative entropies, that at least around 0 and 1, the resulting relative Rényi divergences have to be different. Okay. I would like to show that the whole curve is different, but I don't know yet how to. Right? So I would like to show that if you start from two different relative entropies, then all the corresponding Rényi divergences are going to be different, not only around alpha equals 0 and alpha equals 1. Okay, and when alpha goes to infinity, then we get this kind of expression, which is kind of interesting because even if rho is equal to sigma, if this dq1 and dq0 are different, then this might not be equal to 0. So this shows that for large alphas, this is actually not a quantum Rényi divergence. Okay. So normally these quantities are well behaved when alpha is between 0 and 1, and not when alpha is larger than 1. Okay, it's easy to see that, I mean, we always assume that these relative entropies are finite if and only if the support of the first state is contained in the support of the second state. This is again something that's always satisfied. And then it's very easy to see that this quantity is plus infinity when alpha is between 0 and 1 if and only if these two supports are disjoint. Okay. So just look here, if they are disjoint, then this optimizable, then there is no state that would be such that its support is dominated by both the support of rho and the support of sigma. So this infimum is going to be over the empty set, so it's plus infinity. Okay. So this is really just by the definition, but it has a very important consequence that if we have any other quantum Rényi divergence which has a different criterion for being plus infinity, then it cannot be a barycentric Rényi divergence. Okay. And most of the Rényi divergences that we know are such. Okay. So for instance, the measured Rényi divergence or the alpha Z Rényi divergences, any of them, for alpha between 0 and 1 are plus infinity if and only if the supports are perpendicular to each other. Okay. But these barycentric ones are infinity if the supports are disjoint from each other. Okay, so these guys, they cannot be barycentric Rényi divergences, so these are something new. Okay, they might still be equal to the max alpha divergences, but they are not. Okay, and this would be the last thing that I wanted to explain. So just so we want to explore where these new Rényi divergences are compared to the other ones that we already know. And I already drew that picture. So a few things are very obvious. So if all these things are CPTP monotone, then both of these relative entropies are between the measure and the maximal. Okay? So the corresponding barycentric ones have to be between the ones corresponding to the measured and the maximal. But also these quantities are monotone, so they have to be dominated by the measured alpha and the max alpha, because they are the largest and the smallest monotone Rényi divergences. Okay. And if they are also additive, then we have a stronger Lauer bond, because the smallest monotone and additive relative entropy is the omega-2 relative entropy. So then we get this Lauer bond, and of course we can compute the corresponding barycentric Rényi divergence. And if we further have that these quantities are strictly smaller than the maximal, then we get that these two things are strictly ordered in some sense. And the last theorem that I want to mention is that so one might ask if we can go up to the max Rényi divergence. So here this says that for any reasonable relative entropy, all these barycentric Rényi divergences are above this d alpha infinity, right? Which is this top line of the alpha z plane. So they all have to be above this quantity, and typically they are strictly larger. And the question is if we can go up to the largest monotone quantum Rényi divergence, and it turns out that we cannot. Okay, so the strict inequality means that basically on every pair of non-commuting invertible density operators